So good morning, everyone, and thank you for attending this session. I'm Simona, and today with my colleague Yanki, I would like to present the alerting solution we have implemented to optimize the mainframe apps. So let me first start with a quick outline of this talk. We would first briefly introduce the client environment. Then after stating the goal of the project, we will proceed describing the tools we are using to achieve it. We will then go a bit more into detail on the algorithms we implemented for anomaly detection and alerting. And finally, we will conclude the talk showing you a live demo for the results displayed in Tableau. So our client supports an IBM mainframe platform running multiple DB2 databases, which contain information belonging to different applications. When querying the databases, each one of these applications sends an SQL job. And in this context, each job is referred to as a transaction. Our analysis for this project is done on a transaction level and not on a higher up one. The data we are working on are relative to resource usage and performance of each one of the transactions. The main metric used are, for instance, the get page ratio, the number of SQL queries, or the CPU consumption. And in particular, among these metrics, the most important one is the latter, the CPU. Indeed, the app owners are being charged based on CPU usage. So, as just mentioned, since the app owners are charged according to the CPU consumption, it is of capital importance that the transaction queries are properly executed. Indeed, for instance, if a transaction shows an abnormal behavior that has too high CPU consumption, the cost will spike up. In the past, the client would manually check a sample of this transaction using Excel sheets to look for this abnormal behavior. And our goal here is to implement an automatic solution that tries to find, in the shortest amount of time, those transactions that show unexpected behavior. And in this way, it is possible to check 100,000 transactions at the same time and be able to promptly alert the app owners that can then fix this anomalous transaction. So our solution is based on the usage of a Spark cluster, but it is cloud agnostic, meaning that it can easily be modified to be able to run in any kind of public cloud, such as Google Cloud, AWS, Azure, or even on a private cloud on-prem. The backend development is done primarily using Spark and Python, whereas the front end is done in Tableau. As described in the sketch at the bottom of the slide, each day mainframe data is ingested in the Spark cluster, where an automatic pipeline runs the ETL jobs, and then subsequent scripts are also run to do analytics and alerting. The results are then displayed in Tableau that automatically gets updated with the latest results, so that then the client, the user, is able to have the most up-to-date information. Before proceeding with the rest of the talk, we would like to briefly remind you the definition of anomaly. So an anomaly is a data point or group of data points that exhibit a pattern that deviates from the normal behavior. Anomalies can be classified in three main categories. The first type is the point anomaly. As shown in this picture at the top left, a single data point is called anomalous because it deviates largely from the rest of the data points. The contextual anomaly, as depicted in the middle right, on the other hand, occurs when a single data point assumes a value here that is per se not anomalous, meaning that it can occur also at other points in time, but deviates from the trend here of the points around the point itself. Finally, a collective anomaly is as shown here at the bottom left, is when a group of data points exhibit an anomalous behavior with respect to the other data points. And a single data point within this anomalous group is, however, not necessarily an anomalous one on its own. So, as just said, there are different kinds of anomalies, and to better detect them, we employ two different algorithms. We use a linear regression to detect collective anomalies, and the Prophet algorithm to find point and contextual anomalies. In the rest of the talk, we'll go a bit more into detail and describe the two algorithms and how we created the alerts based on them. So the first algorithm that we use is based on linear regression. In particular, for each transaction, we divide the data set into different parts, to different sets, the present data point and the historical ones. The present data set, here highlighted in blue, consists of all the data points belonging to the time window starting from today and going backwards an n number of days, where n is the interval size. The historical data set, on the other hand, here highlighted in red, includes all the data points of the transaction besides the one that belongs to the interval. Since the frequency of the data points for each transaction is different, we use 4 different interval size, for instance, 3, 7, and 10 and 30 days. And in this way, we can account for different behaviors. To find anomalous transaction, the algorithm first performs linear regression on the 2 different data sets, the historical and the present one, and obtains the slope of the 2 lines. In the picture here, you may see the 2 linear fit for the historical in red and for the present, for the interval present day sample in blue. We then calculate the difference between the 2 slopes and define anomalous, a transaction that has a difference between the 2 slopes above a certain threshold. Every day, the linear regression algorithm is run on almost or more than 200,000 transactions. And as just described, each one is flagged as anomalous or not by comparing the slopes. However, we do not raise an alert just yet. So in order to have a more robust and not a robust solution and not be subject to data volatility, for each transaction, we bin the data taking into consideration the result of the last n days. And for instance, here, the bin size is 10 days. Among these 10 days, we count the number of alerts raised by the algorithm. And we then raise an alert, an anomaly alert, following a traffic light schema. In particular, if 80% or above of the days are flagged as anomalous, we give a red alert. In our case, with a bin size of 10 days, this corresponds to 8 or more anomalies, as you may see, for instance, in this example here in the table below. If the number of days flagged as anomalous is between 35 and 80%, we raise a yellow alert. If the number of anomalies is 3 or less, we have a green alert. To detect point and contextual anomalies, we may make use of the Prophet algorithm. Prophet is a machine learning algorithm developed by Facebook for forecasting time series data. The algorithm models data taking into account seasonalities, missing data, shifts in the trend, and it works at best with time series with a strong seasonality and also with several seasons of historical data. While modeling the data, Prophet provides an interval of confidence around the best fit that is very suitable for anomaly detection of points which deviate from the trend. In this zoom-in image of a portion of the curve that we've shown before, you may see the blue line here that is the best fit done by Prophet, and the light blue area here that is the confidence interval. And we flag as anomalous all those data points that are above the confidence interval. For instance, like these 2 red points that are above this light blue area. Similarly to the linear regression case, also for the profit algorithm, we do not raise an alert if just the last data point is flagged as anomalous. In this case, we take into account the last 10 data points, and we count the number of anomalies as we did before. And again, as we did before, we flag the alerts according to our traffic light schema. If out of 10 data points, 4 or more points are flagged as anomalous, we raise a red alert, as in the example here below. If 2 or 3 points are flagged as anomaly, this is a yellow alert, while it is green in the remnant of the cases. We would like now to show you the results in a live demo in Tableau, shown by my colleague Yankee.
Thank you, Simona. Welcome, everyone. Thank you, Simona, for this beautiful outline. Quickly share my screen. She's the architect and brain behind this sophisticated solution. And we wouldn't have this without her. And thank you to her once again. We created a similar dashboard with a real one by using dummy data. And today I'm gonna show this dashboard, and we will look at visual representation of the results together. Before switching to the dashboard, I would like to mention on one small thing. Each and every day, we send, actually the Tableau server sent 3 emails to the analysts who are looking over to these alerts or maintaining this mainframe database. This is a sample of an email that Tableau server sends. We are using this approach to let analysts look at these alerted workloads, and if they notice something which creates some urgency, they can directly contact with application owners, alert them, and let them to optimize or maybe shut off the application for maintenance right away. At this point, analysts also have the chance to go directly dashboard from clicking here and dig deep into the results. As Simona mentioned, we have 2 algorithms running in the background and pushing the alerts to the dashboard. We have one regression alerts panel, which are focusing on finding the dramatical changes in the workload processes and finding anomalies. Here, analysts have the option to check by hovering over the workload, to check the history and look at if there is a seasonality or a very different or deviant behavior than the historical behavior of this workload. As we see for this workload in the history, like 2 years starting from January 2019, in the last couple of months, we have received a huge jump. That's why algorithm alerted that workload to let the analyst warn the application owners for optimization. At this point, analysts also have the option to focus on, let's say, the prior 1 alerts by limiting the CPU cost for last 15 days, like 100 euro, and focusing on the ones which are creating the highest costs, so that these type of filters will let them to dig or focus on the more important workloads. On the other side, they have also the option to filter by selecting one of the applications and focusing to the alert of these applications. As I said, this is the regression alert dashboard. We have also one profit alert dashboard. This dashboard holds the workloads that were alerted by profit algorithm. We have the same options. We can set a minimum CPU cost. We can filter by application. We can look at the history. But opposed to regression alert panel, we will have another option here. We can, let's say, select one workload. Clicking this button will open us a profit view, where, as Simona showed in her presentation, where we look at the real values, the ones that out the confidence intervals marked as red, the ones inside marked as green. The yellow line shows us the prediction, the best fit, and we have also some future predicted points here. We can maybe zoom a bit down to that area. So that you can decide, okay, this application, this workload will behave badly in a couple of days. At this point, analysts have also another option. As you see here, we are only focusing on one metric, which is the CPU in both dashboards, either regression alert panel or profit alert panel. But they might think, okay, why this workload is being alerted? Maybe there is a reason which is being triggered with another metric in the database, so that I would like to compare this workload with the other metrics to see some correlations maybe. I can click this button to go to the main dashboard, which is shown with home icon on top left. Also, I can use there. As you see now, we focused on in our main dashboard only to this workload. We still put the CPU in the center. We show ratio here. We show this is another metric, takes the ratio of get pages and SQL. Get pages is the results that SQL query is returning on this database, and transactions and daily CPU cost. But in the real world, we have more. Right now, it's not available in this data. And maybe one last point. So we have managed to come to this main dashboard by selecting one workload. We can always reset this action and start to dig or do our own discoveries based on the system. Right now, we are getting independent from the alerts, and we can do our own discoveries. Let's say I have in this dummy dataset 6 applications, and I am highlighting the lines right now. I can see based on the heat map, the highest CPU consumption is happening here. And I can focus on this application by just clicking it. And as I see, there are 200 workloads right now, 221 precisely. I can see the workload level by changing the analysis level here. I can put some, let's say I want to focus on only minimum 1000 CPUs to decrease the result set. And among all of these, I can also check by clicking here. As I see, it's 24 of these 71 applications workloads were also alerted, and I click that. I can focus on this 24 directly on this dashboard as well by not going into alert panel, let's say. I have one final filter or one final chart. We have one CPU cost change chart, which is just overlapping the dashboard. I can see here based on the last day and the previous day, where the highest CPU cost change has occurred, I can see it here right away, which might made me think that, okay, there's a problem here. And probably this is one of these red workloads. Okay, that's all from my side. Thank you for listening.
Yeah, thank you very much. I think we can begin with our Q&A session. The first question we have is, how are the interval sizes for the linear regression algorithm chosen? Are they always the same?
Thank you for the question. I think I can answer that.
Yeah.
So the interval size are not carved in stone. So the one presented in the talk of 3, 7, 10, 30 days are just relative, for instance, to our specific use case. But first of all, the first step is just look at the data, and the most important feature is the cadence of the data, so the frequency. If the workload are run daily or just weekly, we would use a certain windows, interval size. So the smaller, so the smaller the frequency is, the larger would be the interval size. If, however, on the other hand, we have transaction that run every single hour multiple times, we would use a smaller interval size of 1 day or even few hours. And of course, if a transaction changes his behavior in time, this is also taken into account in the algorithms, and the right window size is chosen always according to the frequency of the data points.
Thank you. We already have many interesting questions. The next one is, which type of Tableau connection is used to pull the data from Hadoop cluster? Live connection or extract?
Okay, I can take this over. As Simona mentioned during her presentation, we get the data each morning and in a daily frequency, so that this doesn't require to connect to the database in a live manner, so that we are benefiting or leveraging the sophisticated extract hyper databases of Tableau. We pull the data, we create a refresh schedule, but first at the beginning we pull the data to the extract hyper database, and after that each and every morning this extract database is being refreshed on Tableau server before we send the emails to the customer or the analysts.
That sounds great. The next question is, can you support different backend database engines? We don't use DB2 due to lack of skill set, but we have various other engines covered, like Oracle, Postgre, MySQL, EDB, as well as some NoSQL.
So yeah, thank you also for this question. I can take it. I would say that, yes, in principle, it doesn't really matter what's the source of the data. So if you use different kind of engines, it's perfectly fine. I mean, what is important is the quality of the data and the fact that we do receive the data in a proper way. It doesn't really matter the source. So of course we need to, one would need to check the data itself, but a priori, I don't see any issue, any problem in this respect. So it doesn't really matter.
Thank you. The next question. There are some red marked value labels on panel charts. What do they show or mean?
These panel charts, actually, they are custom visualizations. They are not built in Tableau. We did it by using some workarounds, and there is a specific order in the background. Why you might think why this one workload on top left corner or the others are middle. So we are using a specific sorting there by sorting the workloads based on their last day's CPU values, so that we are showing the high CPU consuming workloads on top of the panel, so that before going down or scrolling down, we are first focusing on the high CPU values. And this last day CPU value, if it is the max value of all the timeline you see on this panel charts, they are marked as red. So that, okay, I need to focus on, especially among all of them, these guys.
Thank you. Sounds great. Next question. Can I have a similar solution on my on-premises cluster? Do I need to use Tableau or can I use my favorite BI tool?
So maybe the first half of the question I can take over, and then let Yankee say a bit more about the BI tools. Yes, so as long as Spark cluster could be built, it can be built wherever the client likes. So it can be on-prem, on a on-prem cluster, or on your favorite public cloud. It's really cloud agnostic. It doesn't matter where it is, as long as the tools are available.
The second part of the question. As far as I know, if you would like to go with panel charts, it's also called small multiples. Power BI is letting you to do the same development. I guess for ClickSense, maybe it would require some extensions, but I'm sure it's not built in ClickSense, which is another dashboarding tool. But yeah, if you use Power BI, you would probably you could create the same structure that I created, since I'm just using line charts on the main dashboard, but the alert panels are just some custom visualizations, and handful of tools are letting you to do the same, actually.
Thank you. Next question is, are the alerts only raised based on the CPU values? Are there other metrics also taken into account?
So I can answer this one. So in the presentation, in the talk, we showed just examples based on the CPU values, because as we mentioned before, this isn't the most important metric, because clients are charged on it. But of course, we take into account, so we do the analysis not just on CPU values, but on multiple other metrics. And we can, of course, alert on each one of them singularly, each one of them, or we can combine the solution for different kind of metrics. So it's the more metric one has, and if one wants to use more metric, this is possible. So it's not necessary just CPU.
Okay, that answers the question perfectly. The next one is, if we have data replication in place, like Oracle Golden Gate, BigLogical, or other, what would we need to do to make sure your ETL process can ingest this data?
So thank you for this answer. I'm not 100% sure I understand this question. So maybe if the person who asked it wants to go a bit more detail, I suggest you one-to-one talk. But if there's replication in the data source, it's not a problem, because in the ETL we make sure to have unique data points. So we make sure that one transaction has one single. So given the transaction ID, giving a specific timestamp, we use just once the metric for that specific time set. So if we have replication, we have this data several times, we just take one of them into account. I don't know if this answered properly the question. If not, please let me know, and I'll try to go a bit more into detail.
Hopefully it answers it. Anyways, the next question is from the same person. Can reports be fed to other presentation layer, i.e. different to Tableau?
I can take this. So as I mentioned maybe in one of the previous questions. Right now, the reports were developed by using Tableau, and we are taking data from Spark SQL tree server. And if you just tie another BI tool, like if you just connect to the same data source by using another BI tool that has access, you need to redevelop these reports by using this tool, because the current dashboards are just Tableau specific. You can embed the dashboards by using embedding codes, or you can share them with your colleagues, but they need to have access to Tableau server. But the presentation layer in our current infrastructure, it is Tableau server, so that you can only use Tableau server to connect, interact, and get your insights from the data.